Hello again. So I'm back to finish the lecture on superconductors. So previously we discussed some properties of superconductors. So today I'm going to complete that lecture on superconductors. So let me get started here. So today I'm going to start talking about applications of high temperature superconductors. We already talked a little bit about these magnetically levitating flying trains. So these have been successfully implemented in many places, including the Central Japan Railway Company. So in these maglev trains, what you have is these superconducting magnets shown here. So then we have these ohmic rails. So because this magnetic field lines trying to penetrate this ohmic rail, so that gives you some repulsive force, so that makes these wheels cushioning from the rail. So that means they are more like not really touching the rails. So this same effect can be actually expected from high DC superconductors. Here we show simple small magnet levitating from high TC superconductor. So this is in liquid nitrogen temperature. So in this here we have similar this levitating effect, right? So that happens because if you have this small magnet, so they have flux lines coming from the magnet, but since this is a superconductor like here, so we know Meissner effect, so you cannot have these magnetic flux lines penetrating through the superconductor. So that means they are going to be expelled from the magnet. So that means these field lines are going to be flattened here, right? Because it cannot go through the magnet even here. So you can see the flattening of the field lines. So this is where this flattening happens, you have a force, right, on the magnet. So that's the reason we have this levitation. So also you can think about this one like having image magnets. So then the two magnets repelling each other, right? So south and south poles, they repel each other. So actually, if you have superconducting magnets, so we can visualize, have a vision about having these maglev trains using high TC superconductors. So another important application of these high TC superconductors is they are used in these colliders, in high energy particle colliders. So they use these high TC superconductors for radio frequency cavities. So another, I think, most celebrated application people are thinking about is the energy transmission, right? If you can make cables from these high TC superconductors, you can transmit power without loss of energy, because you don't have that energy loss due to heating because of the zero resistance. So here people have already made these cables and slabs of high TC superconductors using this typically BISCO and YBCO superconductors. So also another important application people are thinking about is the use of high TC superconductors in transformers for railway power supplies, shown here. So also I think this can be easily employed in these powerful superconducting magnets, right? So this way you don't have to cool it down to liquid helium temperatures. So even at liquid nitrogen temperatures, you can use these high TC superconductors for very powerful magnets. So in scientific and industrial NMR facilities, people are thinking about using these high TC superconductors, especially for pharmacological investigations of various biomicromolecules. These have been already well thought about in Yokohama City University. So also these can be easily used in medical NMR, nuclear magnetic resonance tomography equipment, so to make medical images. So another application you can imagine is in wireless communications. You can make these devices from high TC superconductors with very high frequency filters for these communications. So they can be easily integrated into these control devices. So now let's talk a little bit about characteristics of these high TC superconductors. We talked about this as type 2 superconductors, right? So different from this conventional type 1 superconductors, where in type 1 superconductors you have this one critical field. So above critical field you lose the superconductors, but in type 2 superconductors we have two critical fields. Even above this first critical field, so still you have this it can be in the Meissner state with some vortices and having, we call the mixed states. Usually type 2 superconductors have much higher critical fields and also much higher critical temperatures. So here we already talk about this ones. Type 1 superconductors, you have this one critical field, but in type 2 superconductors, we have two critical fields, right? So this is where you have the mixed state with the vortices. Above the second critical field is all becoming normal state. So most of high TC materials are these cuprates, so that copper oxide planes, right? They are two-dimensional, two-dimensional layers. They are the reason for this high TC properties. Since they are two-dimensional, they have very high, strong anisotropy. So that means you have these parameters are very different from your plane direction and the perpendicular to the plane. Then if you talk about some other superconducting applications, we already talk about superconducting transmission lines. So then also you can make superconducting motors and generators. So then also there's this superconducting magnetic storage devices. We know we are in need of many storage devices, right? So we use hydropower and so battery power, there's a chemical energy storage. So then wind, this power can be stored in batteries and also in other storage devices. But superconducting magnet energy storage also another way of storing energy in this SMES, superconducting magnet energy storage. They store electricity for long period of time in superconducting coils, because superconducting coils, once you have a current, so they can stay there for long time. We call the persistent current, right? So this way you can keep your energy stored for a long time. So then computers, so you can have these high TC superconductors in the form of Josephson junctions. So then, so that will have much less heat dissipation. So also this Josephson junction can be used in not just in the computer circuits. So then other switches and that requires very short switching time, like we are talking about picoseconds or slower. So then squid magnetometers. So this is, we are going to talk about this one later. This is a superconducting quantum interference devices. So they are one of the, so that's actually two parallel Josephson junctions. Though these can be used to detect incredibly small magnetic fields. So even, so that's one of the most sensitive devices. So they can be used to measure magnetic fields even in mouse brains to test their pathological properties. So then this can be even used in this high fault current applications. So when we know when you have lightning strike your devices, so they can be troublesome, right? So that can destroy your devices, but by having this superconducting fault current limiters, you can avoid that kind of damage due to lightning. So because this fault current can be operated at this liquid nitrogen temperature, so that way we can avoid this damage to your system. So then obviously we talk about the brains. Okay, so now let's get back to some theory of this superconductivity. So we know if you consider simple metal, so not superconducting, normal metal, if you look at temperature dependence of your resistance, we know if you have a perfectly pure metal like shown in the bottom curve, so at zero temperature you get to zero resistance. But for high temperatures, much higher temperatures, they show very linear temperature dependence like here. So then that's mostly due to the electron-phonon interactions, right? So then when you get to much lower temperatures, we are talking about temperatures less than this Debye temperature. So then they show something like T to the power 5 temperature dependence of resistance. So that's also coming from this phonon electron interaction, and with some effect coming from electron-electron interaction also. Then if you go to much lower temperature, so they behave more like T to the power 2. That is all about electron-electron interaction, because you don't have any phonons anymore at that low temperatures. But that is typical metal, pure metal. But if you take an impure metal, they still show that high temperature linear behavior, then becoming this T5 or T square dependence, but they don't go to zero resistance at zero temperature. That's because you always have some residual resistance because of the impurities. That can be magnetic impurity or some other impurity. That is typically what you expect from a simple metal. But if we have a superconductor, so this is what we were expecting from impure metal, right? So now if you have a superconductor, so they at this Tc immediately it goes to zero. So this we call the critical temperature. So now if you want to consider further, we need to understand a little bit about how conductors behave in magnetic field. So then we can talk about the superconductive. Here I'm talking about just a normal metal. If you have a normal metal, if I apply magnetic field, we know the magnetic flux lines, they pass through the metal, right? So this is normal metal, no superconductivity. But if I turn off the field, so I don't have any trap field here. So we can explain all these phenomena using these four Maxwell's equation everybody familiar with. So first one is the Gauss law. Second one is basically we are telling there are no magnetic dipoles. The third one is basically the Faraday's law. The fourth one is the Ampere's law plus. So we introduced this something called displacement current. So then also we know the macroscopic Ohm's law, right? So these are the things we need to explain some of the properties So then in normal metals, we already talk about the magnetic field. So how that is B, if I have external field H, so your magnetization M, we introduce the magnetic susceptibility like this, then we write B equals mu H, mu is your permeability. So now what happens if we have a superconductor? So here we are talking about two ways. So in first one we call it the zero field cooling. That means I cool, this is initially at, so if you look at this one, I do this one in two different ways. In the first one, you can see this, the material, they are in purple color. Purple color means they are already in the superconducting state. So here in this zero field cool situation, so first I cool this one below Tc, that means this is already superconducting. Now if I apply magnetic field, what will happen? Since this is already superconducting, so Meissner effect, so no field can go through the superconductor. So this is the exclusion of magnetic field. Now if I remove the magnetic field, you don't have any trapped magnetic field here, right? So second one we call the force cooling. That means first I apply magnetic field when it is under normal condition. You can see this is not superconducting. So this is already normal metal. So I apply magnetic field. So the magnetic field lines will pass through the normal metal. So now if I cool, what will happen? Still, since now it becomes superconducting, I cool below Tc. So then this magnetic field still, since it is superconductor, it cannot go through the the superconductor. So again, Meissner effect. So now if I remove the magnetic field, so you don't have any trapped magnetic field. But if this is a magnet, normal metal, so then if you have magnetic field, so then you can see even if you remove the magnetic field lines, because of the Faraday's law, you will have some induced current, right? You can have current trapped magnetic field here. But for the superconductors, no matter how you do, whether you first cool and apply magnetic field, or first you apply magnetic field and cool, the zero field or field cool. So both ways you don't have any magnetic field when you switch off the magnetic field. Okay, so then in this situation, so if you use that equation, if superconductors are perfect diamagnetism, so that means your susceptibility is -1, then your M is -H, right? If I plot H versus -M, so then you have this straight line. So this is below Tc, or below, sorry, this is you are plotting with respect to H. So below Hc, this is for type 1 superconductor. You have superconductivity, that means M equals -H. Above Tc, there's no superconductivity, then it will have only this simple diamagnetism, but we know that's very small, almost zero, right? So then if I plot B versus H, you can see for the superconducting state, your B is 0, right? That's that magnetic flux or induction. So, but when you go above, so that means it becomes simply normal metal, then B equals μH, right? That has simply this B equals μH relationship. So everybody should know how B and M changes with H. So now let's talk about the superconducting parameters. So if we know if you have a magnetic field, we have an energy density, right? So energy density is given by B squared over 2 mu. It's very similar to if we have electric field, we have electric energy density of half epsilon E squared, right? So now if you consider your this Helmholtz free energy, so it can be Helmholtz or Gibbs free energy, doesn't matter. So if you plot as a function of H, we know in the normal state, it is pretty much independent of your magnetic field. But in the superconducting state, we know, so above this critical field, that is becoming normal, right? So that means So until this is my HC, at HC it becomes normal state. So below HC, that means it's in the superconductive state, you have this kind of behavior. So at H equals 0, that difference is basically your this magnetic energy that is given by d squared over 2 mu. So that's important thing to remember. Now let's start talking about the London theory of the superconductor. So that is basically we have simply used Newton's law under applied electric field. So we are applying electric field. So then in the superconductor, we basically have the supercharges, right? These are Cooper pairs. So the charge of the Cooper pair is actually 2 times E, right? So now if I write my Newton's second law, total force is given by M. A is dVs over dt. So Vs is the velocity of your this supercharge. That's more like the 2E Cooper pair velocity. So now, so we can relate Vs with the current density. Everybody remember current density, supercurrent density is given by NSE Vs. So here now we can replace Vs by Js divided by NSE. So that means also F force is given by, since I apply electric field E, so your force is E times E. This equals M d over dt. Then Vs I can write that J over N. So now if you take E is, you can write as d over dt. So if you divide by E, you get E squared. So that is you get M over ns E squared times Js, right? So this I write this gamma as M over ns E squared. You can see this is if you divide by E, you got E squared, then you have ns. So this gamma is M over ns E squared. So now I can write this is basically dJs over dt equals this ns E over M, right? So this basically you just take gamma out. So then dJs over dt equals, so this is in terms of these parameters here. That's simple to show. Now I take the cross product with respect to grad. So I take grad cross of both sides. So grad cross of this one, grad cross of dJs over dt. So if you write this one, what is this part? So this is a constant nsc squared over m. So then grad cross E is Faraday's law, right? That is minus dB over dt. So that is simple. So then grad cross this one. So now if I take the, you can see this both with respect to time. So I can take d over dt common. This is grad cross Js plus nsc squared. This is fine, right? So now since this is 0, we can have this inside this 0, because we know inside the superconductor your magnetic field is 0. Then I can write grad cross Js equals minus this one, right? That's the starting point. So now if I go, so this is what we so far, right? Grad cross Js equals this one. Now I'll start with the Ampere's law, the fourth law of Maxwell's equation. So that is grad cross B equals this one. But here there's no displacement current, so we can forget about this last term. Then if I take grad cross of both sides, so this is 0, then grad cross B equals mu 0 grad cross J. So now what is grad cross B is, we know that you can write as grad dot B minus grad squared B. So everybody should know this identity here. So vector calculus. So this you can write as mu 0, but we know grad cross is minus. So this part I can write as minus ns E squared over mb. So if you write this way, so we know grad cross B is 0, right? This term is 0 from that second law of Gauss law for the so second Maxwell's equation. So then what I get is this grad squared B equals mu 0 ns squared mb. You can see this is a second order differential equation, right? If I write this term as 1 over lambda squared, I can write this one as z squared b equals 1 over lambda squared b. So everybody knows. So here lambda squared is this one. So we know this solution for this one, that you can write as b equals b0 e minus z over lambda. So b is in the direction of c. So you can see this is exponentially decaying magnetic field. So B decays like that. So C lambda is actually the penetration depth, right? So that's what we showed, right? We know in the superconductor, the magnetic field doesn't go to zero immediately. It goes through this penetration depth. So we can calculate that penetration depth. Actually, derivation is very simple from the London's theory. So screening not immediate, that's what it says, right? It doesn't screen immediately. It has a characteristic decay length. Typically, this length is about a few tens of nanometers. So you can easily calculate that lambda, since we know M, that's MEN. If you know the supercurrent density, we can calculate your lambda for any given material. Okay, so now let's get back to Ginzburg-Landau. So if you remember, he first considered, Landau first started the theory without considering any magnetic field. Then later Ginzburg came along and introduced the magnetic field. So he introduced this order parameter psi squared. So actually that psi squared is same as your supercurrent density, Ns. So that's associated with the Cooper pair density. So now what he did was he expressed F, the free energy. It can be Helmholtz or Gibbs free energy. So that's superconducting, and the normal that he wrote as alpha times psi squared plus beta over 2 psi 4. So yeah, so this is actually for zero magnetic field. So if you write this equation, so we already discussed about this one. So if you take this alpha as a positive number, so you get this curve with one minimum. But if alpha is negative number, you see this curve that has two minima and one maxima. So that's the more interesting situation here when lambda is a negative number. So to find this position of this minimum, you can take the derivative of this Fn and make it 0. If you do that one, you can see if you differentiate this one, you get 2 alpha psi, then you get 4. Actually, differentiate with respect to psi squared, right? So if you differentiate with here, you get alpha, then you get 4 alpha squared, right? So because you are differentiated with respect to psi squared, so then you get that value at where it is minimum is given by minus alpha over beta psi squared. So we call this one psi infinity. So that means you have two values, right? So this one and this one, the magnitude is given by minus alpha over beta. So now if you want to find, so this is that minimum value. If I want to find the value at this point, the minimum value, then you have to substitute that value, what is the psi squared value. I need to find what is the value of Fn minus Fs. Just substitute that psi infinity value here from this psi squared and psi 4. If you substitute, you get minus alpha squared over 2 beta. You can easily find this one. So now we know the superconducting parameters. We found that the energy difference between the superconducting and normal state at zero magnetic field is given by this 1 over 2 mu 0 b squared, right? B squared over 2 mu 0. If you equate these two, you can get that critical field given by this one. That's it. This is still at zero magnetic field, right? So then came along Ginzburg. So he introduced this magnetic term non-zero magnetic energy B squared over 2 mu 0, and also his Hamiltonian, he included this quantum momentum, everybody remember this one, but in this P, he also introduced this vector potential term. So you have this, this is the now Landau-Ginzburg theories. This is what Landau proposed, right? He had only this term. Now Ginzburg introduced additional term coming from the energy, magnetic energy, plus this Hamiltonian term, that is, we know energy is given by 1 over 2m, your P squared, right? P is now minus IH grad that we know in quantum mechanics operator for momentum, plus then he introduced this vector potential term QA, but A is given by the grad cross A is your magnetic field B, right? So if you introduce that one, you can easily get this relationship. This is the Landau-Ginzburg equation. So now if you write the total free energy, so this is the equation. Now this is a more like a functional, right? So what you have to do is you have to take the delta f of this function, so the functional derivative. So if you make it 0, you can find the maxima and minima. So then when you do this one, you can do it two ways. You can take the derivative with respect to psi star, because psi squared means psi times psi star, right? So if you take with respect to psi star, so then you get this equation. If you get psi star, then you get alpha times psi, then beta. Here you get psi squared psi. So you can calculate this one. So then to find minimum, you can make it 0. So you get one equation there. Then you can also differentiate with respect to A. This is your vector potential. So here, find distribution of the order parameter psi, and one has to minimize this functional with respect to these quantities, with respect to psi star and A. So then make it 0. So then second equation, if you take the derivative, you get this equation. You can easily do this one. If you, with respect to A, you can see this, you have psi star, then 2E terms come in here, divide by M. You can easily find that one. So this is your, then that is your, when you take with respect to A, right? So then if I want to find my current density, you can use this equation, right? Your grad cross B is given by grad cross B is grad cross A, that is mu naught J. From there, you can calculate your J, you get this expression. So if you look at this expression, this is very similar to the probability current density in quantum mechanics, right? So that means this expression, the second expression, indicates that the order parameter is really has a meaning as a wave function. So in quantum mechanics, we use the simple Schrodinger equation. So then we get this term without A, right? So what you get is 2E over M real psi star, then this IH cross grad psi, right? So that's the probability current density. Now you have additional term coming from the vector potential, but by looking at this one, you can see your order parameter psi has the very similar physical meaning as the wave function of your Schrodinger equation. So now if you look at that first equation, so that is when you differentiate that with the psi star, you get this expression, right? So now if you take this psi gamma, we know that one. So now if you divide everything by that psi gamma, you can easily write the expression like this. Now if I write this psi over psi gamma as some different psi function, you can actually get some very symmetric function like this. So, but if you can linearize this function, you get grad squared psi equals minus 2 over this one. So you can see this is again second order differential equation. This theta we define as this function that has that this number alpha. Remember that alpha is a negative number, right? Because to get that 2 minima, we had to use negative number. So now you get this second order differential equation. So that one, so that is this one. So this one also we can solve for theta. So if you solve, so this is very similar to lambda, but in this case we know that theta is increasing through the superconductor. So this is your vacuum, right, outside the superconductor. This is inside the superconductor. We are talking about this the order parameter, right? So there's no order parameter in vacuum. So but in the superconductor we have this order parameter psi, but that one also, like the penetration depth, it doesn't happen immediately at the boundary. It develops or inside the superconductor with this characteristic length of theta. So previously we had something with lambda, right? So now it is changing as a function of this theta. So you can see there are two very similar parameters. One was lambda. Lambda says you how the magnetic field is decaying inside the superconductor. So then this theta tells you how this order parameter develops inside the superconductor. So that is governed by this theta. We call this the coherence length. So this coherence length, that the magnetic field which goes to 0, that we call penetration depth. So this lambda and theta, they are the reason how you can categorize this type 1 and type 2 superconductors. So coherent length and this penetration depth. If you have some material where this coherence length is greater than square root of 2 times lambda, we call that is type 1 superconductors. If your theta is less than the square root of 2 times lambda, we call it a type 2 superconductor. So this the ratio between the coherence length and the penetration depth determines what kind of superconductor you have. Everybody should remember the B field is going like this one, right? B0 minus x over lambda. Also lambda is given by this one. Remember superconducting this current density. Okay, so now we have these two situations here. So type, so here, so I draw one for the situation where the coherence length is much larger than lambda. That means this is coherence length, right? How the order parameter develops, that is theta. This is much bigger than this lambda. So that is how the magnetic field is decaying. So look at the situation where theta is larger than lambda, and in this case theta is very small, right? So here you can see theta is small here where the order parameter develops, and here the magnetic field decays at longer penetration depth. So here lambda is much larger, here theta is much larger. Now we can look at how the surface energy changes. So if you have the situation where theta is much larger than lambda, so that is this one, right? Theta and is lambda. So you can see if I take the what is called the energy. So energy is related to, suppose if I have this coming from your lambda has shorter length, right? So that tells you the magnetic energy, right? So because lambda is related to the magnetic energy, so that you can see this red curve is related to, because that's lambda is small, so you have this curve happening here. So, but for the superconductivity term, so that happens due to the coherence length. So you can see coherent length is much larger. So that means if I write the energy, that goes like that. So now if you take the 2, you can see this one has much higher energy, right? Because this part. So that means, so this is the, you can think about this part as the energy penalty for excluding magnetic field, because there should be some energy to, some energy penalty to exclude the Meissner effect. So then also there will be energy gain to be in the superconducting state. These are the two competitions, right? So still we are talking about the magnetic energy of this B squared over 2 mu. But here you need to understand, one is the magnetic energy is basically to energy penalty to exclude the magnetic field. So this energy is energy gain being in the superconductivity, because that's a low energy state, right? So now you can see, if you look at this area here and area here, this has much higher area, right? So if you take the difference, you can see this is the energy difference. So this is actually penalty, right? So this energy is net energy is a penalty. So that is happening at the interface between the superconducting versus normal interface. So this is the net effect is a energy penalty. So that is for theta is greater than lambda. So, but in the situation where theta is less than lambda, so because in this case your the magnetic field is happening at longer length scale, so you have this curve because that is longer, but this superconducting energy gain happens at shorter scale, right? So now you can see this one has much higher area compared to this one. If you take the difference, so this one has net energy gain. So net energy gain at the surface. So that's the reason why we have this type 1 and type 2 superconductor, because in one case when you have this net energy penalty, that is when this lambda is much smaller than your coherence length. So we call this the ratio we define as lambda over theta. So that kappa is less than 1 over square root of 2. So that we call type 1 superconductors. So in the type 2 superconductors, where you have lambda is much larger than, so there you have net energy gain being in the superconductors. So that means if kappa is defined as this lambda over sigma, that kappa is greater than 1 over square root of 2. So now if you compare, so typical type 1 superconductors are the standard BCS superconductors like alumina, lead, tin. So they have much larger coherence length compared to the London penetration depth, right? Because lambda is much smaller than theta. So, but they have very small transition temperatures and also very small critical temperatures. But here we are talking about only one critical temperature, right? But if you look at this type 2 superconductors, actually was predicted by this Abikosov. So these are mostly these alloys, right? Like YBCO, magnesium diboride, or even niobium tin. So they have these vortices, right? In this case, your theta is much smaller than your lambda. So because we know these ones, so but they have much higher critical temperature and also much higher this critical field. In this case, we have these two critical fields, right? So you can see the difference here. So then, like we discussed, so this type 2 superconductors where your coherence length is much smaller than your penetration depth. So they have like these vortices, right? So we have superconducting regions, then they have these vortices where they become non-superconducting or normal states. And at that point, you have magnetic flux passing through that one, right? Everywhere else here is superconducting. This no penetration of magnetic field, but in other areas you have penetration of magnetic flux. So you can see this is the magneto-optical image of that one showing the your flux lines penetrating through the superconductor. Okay, then last thing I want to talk about is the flux quantization. So this is, like I said, if you have this ring structured superconductor, your magnetic flux, so that is given as B dot dA, right? So they are always quantized in terms of this phi 0. Phi 0 is given as H over 2E is a fundamental constant. So that is actually given by this number 2 times 10 to the power minus 15 volts second, so or Gauss centimeter squared. So typically Earth's magnetic field is about 500 milligauss, right? So if you have 1 centimeter square this area, so there are about 2 millions of these 50 values, right? So you can imagine if you have much higher magnetic field, so how many these flux quanta you will have. Total, these are but the important thing is they are only integral number of this fluxoid. So people have observed this fluxoid in this kind of material. So they studied, measured the flux coming through some superconducting ring. So when they measured, they found this flux. If you divide by this Hc over 2e, that fluxoid number, they found all these numbers comes like either 1 or 2 or 3. So these are quantized flux numbers. These were published in 1961 by this Deaver and Fairbank. So you can easily derive this flux quantization equation. So just assuming if I have flux, so then we have, if you change the flux, we have a supercurrent, right? So because that's a Faraday's law. If you apply a magnetic field, so initially zero magnetic field, now if you apply magnetic field, we will have a supercurrent, right? So, but that supercurrent cannot stay deep inside the superconductor. You can have at the boundaries, but when you go deep into the superconductor, that Js is going to be 0. So if you look at this line integral, that this number should be 0. So that from that you can easily derive the flux quantization equation. So this is where the starting point. You're deep inside, your supercurrent is 0. So you can start, everybody know your current density is given by this Q n times V, right? So, but n you can write as psi squared psi in this vector Schrodinger waveform. So then you're the order parameter, that is we can write as square root of n times ei theta, right? Because we know psi squared is given by n. Because if you take psi and psi star, you can see that becomes n, right? Because eit, e minus it cancel. I write my psi as this one. Then v, you can write as 1 over m, your this momenta with this gauge invariance introduced in the atomic, the vector potential. So then also we know P is given by this quantum mechanical operator IH delta. So now I can write this Js here with this one. You need psi star, you can plug in this number. So then V, you can plug in this number with this operator delta coming here, then psi is again here. So then you have to operate delta on psi star on psi, and you can keep working on this one. It's very simple. Then when you do that one, because you have theta here, so then work in delta on that psi, you get delta theta. So if you do this one, you get this delta theta. Then you have this Q coming from here and H cross C coming from here. So then you get this term because you have A here, right? So from here you get this one. So you can easily show by plugging these things into this equation, you get this equation. Very simple. So now everybody knows this line integral A dot dl, but we know that is equal to this surface integral of B dot ds. So then I can write delta theta dot dl is, so this is B dot ds. So then also this delta theta or delta L I can write as this d theta, you can write as d pi over dt times d pi. So this is, if you integrate from, because this ring, right? So you can go from 0 to 2 pi. So this becomes simply this theta 2 pi. So if you do that one, this is simply, you can write as 2n times pi, right? So that is this the left-hand side, but right-hand side is Qs over Hc times your B dot ds. B dot ds is simply flux, right? So then I can write this Qs over H cross C flux equals this 2n times pi. So if you do that one, you can see Qs, this one, this flux equals 2n times pi. That means this is pi, because that is B dot ds, right? That pi equals, you can see n H cross C over Qs. So this Qs is the fluxoid given by that Hc over 2e. So this, because here Qs is actually 2 times electron, right? This is a super current charge, right? So that's Qs is really 2 times E. So that's what we call the fluxoid. Your flux is n times your flux of pi 0. Pi 0 is Hc over this Qs. Qs is basically 2 times E. Okay, so next, actually, I can quickly finish this one. Next, we want to talk about the Josephson junction. So the Josephson junction is basically if I have one superconductor, superconductor 1 and superconductor 2, so separated by barrier. So it's some weak link between the two superconductors. Now we are going to apply some electric potential here. So then what will happen? So because this, you have order parameter here, then order parameter here. So then you can have the mixing of the two order parameters, right? So that will basically allow some these Cooper pair charges to tunnel to the barrier. So if I write the Schrodinger equation for superconductor 1, I can write as the time derivative Schrodinger equation H cross d psi over dt is, so my potential is suppose V. So then I can write this one as V over 2, right? Because it's shared by the two superconductors times your Q times your, that is your potential term, times Schrodinger, the wave function. Then you have coupling term, so coming from side 2, that I can write as some constant time, the order parameter or the wave function from the superconductor 2. So same thing I can write Schrodinger equation for the superconductor 2, IH cross d over dt psi 2, that is the this one equals, again, then this should be minus q over 2, because when you subtract the 2, you should get V, right? So this is charge times your potential, V over 2, but for the that wave function psi 2, but you have coupling term coming from the superconductor 1. I can write this one as a psi 1. So now you have two coupled equations. You can easily, so these are the two equations. So you can write psi 1 as this square root of n1 e I theta 1, psi 2 as square root of n2. This is the order parameter how we write, right? So now if you plug in, so you can take the first derivative of this one here. So then you can take the first derivative of psi 2. If you plug in this one, you get these two equations. Now you can separate the real and imaginary parts. So that's a very simple thing to do. So if you do that one, you get one equation like dn over dt as this one. So dn over dt as this one. So then I have this, if I take this, you have e I theta minus e minus I theta over 2i, you get sine function, right? So this is very simple to derive. And same cos delta you can get as e I theta plus e minus I theta divided by 2. And so you can calculate all these functions. So delta is actually simply that's theta 1 minus theta 2. This is very simple to derive these equations. So if you put this one, then I can calculate my J. So J is basically if you know J is given by your E n, so then that is your charge, right? So charge, if you divide by your time, you get your current. So because N1 is the super current. So sorry, yeah, super charge. So then if you take the divide by time, you get the current, right? So then you can calculate your J. So just by multiplying by Q. So because this one is basically N, so then you have, there's no charge term here. You have to multiply by charge time term Q. So you get the Josephson current this way. So we write this whole thing as J0. So then your Josephson current is J0 sine delta. You can see even if I don't have any electric potential, you will have some Josephson current. So that's also the sinusoidal curve, right? So that means this is even without zero voltage, you will have AC the current. So that's called Josephson current. So important thing, then also we know this delta, d delta over dt is q v over h. So then delta t is given by delta, if you differentiate, integrate this one, so you have delta 0 plus this one. So this is where I'm going to introduce zero voltage and a finite voltage. So let's start from here. So if I, in this case, if I have some finite voltage, so if I apply some finite voltage, you will see this sine function is going to average out. So then, but if I don't have any V value, so then I have my JDC is, look at this one. So if V is 0, JDC is given by J0 sine delta 0. So that is finite current, right? So that we call DC Josephson current. So because if I apply some voltage here, if you take the time average in, actually that term is going to be 0. You don't see any DC current. So you might see some AC current, but not for DC current. This is very important thing. So, but if you want to take the AC Josephson current, then you need to apply. So here we put some AC field. So V0 plus some small modulation coming from omega t. So then you get AC current like a sinusoidally varying with respect to time. But important thing is, yeah, that's, I need to show this. Important thing is that you don't see, actually I need to show that one is, if you plot your IV, suppose this is my I and this is my V. So when V is 0, you are going to see this current. So you are going to see this current, goes plus and minus. This is your J or I DC. So, but when you apply voltage, it becomes 0. You don't see any current here, 0, until you get to your this critical voltage. At that point, you are going to see some current that is more like standard. This same thing in this side also. So when you get this side, then you have the standard linear IV. But you don't see any finite voltage current for any voltage. Only you see the 0 voltage current. This is we call the DC Josephson current. This is very important thing to understand. Okay, so finally we need to talk about squid magnetometers. Squid magnetometers are basically two Josephson junctions, this one and this one. So connected in parallel. So you can see this. If you look at this one, this is basically superconductor, and barrier, right? So superconductor, and barrier. So now we are connecting this one as a loop here. So now, if then we are going to apply some magnetic field through this loop. So then what happens? So if you look at this one, you can think about this. Remember that the phase difference between these two loops. So if you have one going in this direction, and other one going in this direction. So if you look at that going from P to Q, so you can write your total the Josephson current in the loop, in the A loop. You can write that one as going from P to Q this way, other one going from this one P to Q, but this goes in this direction, and this one goes in this direction. So if you look at this A dot dl, then this is B dot ds, that is phi, but that is negative phi by 2. This is positive phi plus 2. Now if I add this J plus JB, so you can write this one as this function. So you can see this is oscillating as a function of this Q pi over H cross C. So this is very, so this one. So you can see very small magnetic field. The current is oscillating very periodically. So from here you can measure your very small magnetic field. So typical, this is how a standard Josephson junction looks like. You can see this is one Josephson junction. That means you have one superconductor, another superconductor separated by barrier. Same thing here. You have two superconductors separated by barrier, but they are connected in parallel. Okay, so that's all. I'm going to stop here. Yeah, you had called me. Yeah. Oh, okay. Oh, yeah. Actually, I talked to him. Yeah, so he said, actually, he was planning, yesterday he called me, he said he cannot make the presentation, so he will want to postpone to next semester. Then he was asking whether we can support him for next semester. Yeah, so then I said, no, so you have time until Friday. Yeah, I know, yeah, right. Yes, yeah. Yeah. I'm sure. Yes, yeah. So, yeah. Exactly. Yeah. I know. So, no. So I was pushing so hard to get that abstract. So, so finally, yeah. So then, yeah. No. Exactly. Yeah. No. Exactly. Yeah. told exact. Oh, I don't know how many emails I sent to him telling that. Then I had to talk with David Brown and make sure it's okay to defend this week. So finally he agreed. So after talking, lot of things I had to go through to make this happen. Yeah, yeah, I know. Yes, yeah, yeah. So yesterday he called me. Take, yeah, look at that. Yeah, I know. Yeah, that's exactly. Yeah, because just day before the defense, so he said he has this eye surgery or something, right? So this is so difficult. The Jinju, that's why they postponed that previous one. He had to go to, yeah, so he sent email saying he had to go to Cincinnati. Yeah, yeah. So that's, yeah. Exactly. I explained to both of them. Yeah. So I told them we need to advertise this, and so right, 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 right. I know. I can understand. Yeah. I see. Yeah. Oh, right, right. Yeah. Right, right. Oh, yeah, yeah. Right. Oh, yeah. That's no, no, exactly. Yeah, yeah. This. Yeah, I think we need to do that one definitely. Yes, yeah. Yeah. Yeah, well, that's fine. Yes, yeah, 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 something exactly. Yeah, 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 yeah. Exactly. Yeah, yeah, yeah. So why did he agree to that day, right? If he knew the surgeries don't come like, yeah, that's the problem. Yes, yeah, yeah. Right, exactly. Yeah. Like tomorrow, I have. Yeah. I know, yeah. So I had then David had to talk to Kurt Nicker and so a lot of things. So fine. Kurt Nicker, yeah, yeah, yeah. Oh, exactly, yeah, yes, yeah. So finally, I think that's maybe he was not ready. Also later, I found that that excuse was not really the case. Probably he wasn't ready. That's what my feeling is. Yeah, yeah, yeah. Exactly. You have to learn new. Exactly. Yeah. No. Oh, sure. Yeah. No. Exactly. Oh boy. Especially that's a chemistry. Yeah. Even the words. Exactly. Yeah. Yeah. No. Yeah. Exactly. Yeah. Yeah. The some even the language, right? So that's different. Yeah. 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 I'm sure. Yes. Yeah. 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 He is very. Oh, he is very big. Yeah. That I knew the very beginning when he started working. Yeah. 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 Right. Right. Yeah, yeah, do exactly. Yeah, 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 yeah. Oh, exactly. Yeah, yeah, yeah. No, no, I think. Yeah, actually, he sent me one CV from a Chinese student. He has a very poor, yeah, so very poor TOEFL. Yeah, exactly. Yeah, yeah. I should not even look at that. Yes, yeah, yeah. No, yes, yeah. Right. Yes, yeah. Exactly. Yeah, yeah, yeah. Get exactly. Yeah, we have so many applicants. Yeah, right. Yeah, yeah. Done exactly. Yeah, yeah, exactly. Yeah, yes, yeah. Yeah, yes, yeah. Right. Yeah, I didn't even look at that. Yes, yeah, 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 yeah. Exactly. Yeah, yeah. Right. Yeah, yeah. Oh, more than oh, yes, yeah. Oh, yeah, yeah, yeah. We don't want to do more than that. Yeah, yeah, yeah. Right. Yeah, yeah, yeah. Right. Yeah, 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 yeah. Exactly. Yeah, yeah. Yeah, I think we have. Good, exactly. Yeah, 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 yeah. Exactly right. Yeah, yeah. That's all. Yeah, we can do. Yeah. Oh, okay, that's good. Yes, yeah, yeah. Right. Yeah. Yeah. Okay. Yeah. Yeah. Yesterday he called me. Actually, when I was in the lab, he called me. Yeah. Yeah. Exactly. Yeah. Yeah. Physics. Yeah. I told him. Yes. Yeah. 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 So anyway, that weight room he got that official letter also from chemistry for GTA. Yeah. 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 Oh, yes. Yeah. Yes. Yeah. That too. Yeah. So, I don't think. Yeah. I think in the future we should note this one. Yeah. Yeah. Exactly. Yeah. Yeah. Exactly. Yeah. We should not do that. Yes. Yeah. 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 You told me. Yes. Yeah. Yeah. Exactly. Yeah. Yeah. Exactly. Yeah. Yeah. Still, yeah, she hasn't even, yeah, she hasn't even reached out to me. Yeah, 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 yeah. No, that's the thing, right? So most of, yeah, exactly, yeah. I can learn to understand you much better if I can get familiar with the way you right, talk. Yeah. I need your permission to help. Yeah, yeah, exactly, yes, yeah, 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 yeah. Yeah, I told him yesterday, yeah, 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 right, yeah, yeah. Who? No, 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 not yet. Yeah, 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 yeah. You told me. Yes, yeah. Which one? Abstract he sent last time because we had planned this one for this Tuesday, right? Actually today. Yeah. Then yeah. So last week he said it was cancelled or something. So probably not. Yeah, yeah, yeah. Probably yeah. Sergio yesterday actually. Uh, Wondering, yeah, whether that's taking place, right? So he didn't know, I'm sure. Yeah. So that then I asked Ilsikart, why didn't you let the committee know? Then he said, he wrote to Sergio, but Sergio didn't respond, something like that. I don't know. Yeah. Oh yes, yeah. Several times, yeah. Right, exactly, yeah. Committee, exactly, yes, exactly, yes, yeah. No, if you tell him, he will immediately, exactly, yeah, yes, yeah, right. No, right, yeah, yes, yeah, exactly, yeah, right, exactly. No, I gave all those instructions to him. So what to do? Yeah. So he didn't do it. Yeah. Right. No. So actually, I was also kind of wondering yesterday whether I didn't get anything and they have anything, but yeah. Yeah. So that's what I asked him to. Yeah, yeah, yeah. Even I haven't met him. Yeah. So I don't know him either. Yeah. So he's yeah. Right. No, exactly. Yeah. So even I haven't met this new guy. Yeah. I know, that's very strange. Ooh. Oh, I was very, because I helped her to bring some of his students and postdocs here. So I wrote some letters also for her because yeah. So one student actually, Frank Sampon is student, so he finished his PhD, then now he's a assistant professor in Argentina. So he used to come and do some work here in my lab. Yeah, Francisco or somebody. Yeah, so I helped him to recruit some students also here. Wrote some, yeah. So yeah, she was. Why didn't I know? That's very strange. That also you told me. I didn't know. Yes, yeah. Right. Then you found. Right. Oh yeah, that's it. Oh, oh really? Oh, I see. Yeah. Oh, I see. Print. I see. Oh, really? I see. Yeah. Okay. Yeah. Oh, definitely. Yes. Yeah. Oh, okay. Oh, she wants to think. Okay. Yeah. Right. Yeah, exactly. Yeah. That's not his job. Yeah. Yeah. That's why don't they do that? Because yeah, even Bob. Right. That's it. Right. That's it. Because Bob Buchanan. Yeah. Yeah, exactly. Because yeah, Buchanan and Grepper House, we recently published a paper, so we were talking over the phone. So they never mentioned anything like that. That's yeah, that's good. That's very yeah, exactly. They don't care about yeah. No, no, but still you should let people know. That is very strange. Yeah, that's a yeah. Yeah, we were talking about her. Even but yeah, I know. That was October something. Oh, yes. Yeah. Oh, really? Okay. Yeah. Yeah. Right, right. Oh, maybe. Okay. I see. 15, okay, yeah. That's very sad, yeah. Yeah, she was very friendly with me, yeah. Yeah. Very nice person, yeah. Yeah. It's very strange. Yeah, it is, yeah. You know. Yeah, yeah. Exactly, yeah, yeah. Now we cannot. That's right. Yeah. Okay. Yeah, exactly, yeah. Oh, yeah, but still we should know exactly, yeah. Hmm. Very strange, yeah. Chemistry is, I don't know. That is crazy, yeah. Mm. That's really bad. Yeah. So, yeah, exactly, yeah. It's chemistry is not, that's really bad, yeah. Okay, yeah, okay, yeah. Okay, yeah, okay. Yeah. I was on the phone with him so many times. Yeah. Yeah. Okay, bye. Yeah.